Where's Stan? Can you see? Okay. Am I ready? Yeah.
I'm ready.
Okay. All right. So our next talk is by Michele Pasqua on domain precision and Galois connection-less abstract interpretation. So take it away.
Thank you for the introduction. In this talk, I want to give you an idea on how we can check precision in abstract interpretation, for instance, by using static analysis, and how we can do it for Galois connection-less domains. So domains that are not connected by Galois connections, that are not defined on Galois connection, that are used in practice. But before that, I want to give you an introduction of the problem and the motivation. I don't know if you see my pointer. I don't have Roberto's nice fancy pointer, but so software is everywhere. So we have IoT devices all around, spread all around the world. We use programs in healthcare systems, in airplanes, and of course, programs may be buggy, and especially in safety-critical systems, this is a problem because. Oh, sorry. Okay. And bugs in safety-critical application may harm human life, so there is an ever-increasing need for correctness, for methodologies and tools to check correctness of programs. And of course, we want to check the correctness of programs as early as possible, hopefully before production. For instance, we can use testing to check the correctness of programs, but for instance, in safety-critical applications, we want something more. We want correctness proof. So we want to distill a mathematical proof that says that our program is correct. And so in some program analysis, we want to build these objects, and the analyzer that takes a specification that basically say what does it mean to be correct, and takes a program and output, do some computation here, and output yes, the program is correct, or no, the program is not correct. Of course, this object does not exist in general because we have some mathematical limitations, and the analyzer usually can only provide the proofs for correct programs, or it says, I don't know, I'm not able to show you a proof for the program. But this not implies that the program is incorrect. And the one problem of sound program analysis is false alarms. So we have correct programs that is marked as incorrect by the analyzer. So we have a false alarm. And false alarms are a problem because we cannot fully trust the analyzer if the analyzer outputs a huge amount of false alarms. So it is not useful in practice. And in some program analysis, you very often use abstract interpretation in order to define your analyzer. So in abstract interpretation, you have the concrete domain where programs live, and where we want to check the correctness. We want to prove the correctness of our programs, but this is a quite complicated mathematical object. So we have this other more simpler domain when we can prove we can prove the correctness of programs in an abstract way. And the concrete and the abstract domain are linked by Galois connections. Basically, we want to mimic the concrete computation in the abstract world, and because in the concrete domain we are not able to compute the semantics of our programs, so we jump in the abstract, we compute program semantics in the abstract domain. We are able to, hopefully, compute this object, and then we can prove this decidable check. So we have this decidable check that basically say that The abstract semantics imply the abstract specification we want to prove, and this implies the concrete undecidable problem we want to prove. Of course, this is a simple implication, so we have false alarms. And basically, the analyzer computes the abstract semantics. But of course, here, as also Roberto said before, we have two sources of false alarms. We have one source that is the abstract domain, so how much abstract is the abstract domain, and the abstract computation. So we have two sources of imprecision, let's say. And this is, of course, unavoidable unless we change the domain, but we can check the imprecision of the abstract computation. This is a classic notion of completeness. So completeness basically says that we don't have a precision loss in the abstract computation, and it is defined on these commutations here. So if we compute in the concrete domain and then we jump in the abstract, or it is the same as first jumping in the abstract domain and then computing the abstract function. So we don't have a precision loss in the abstract computation. This is the toy example that Roberto used, but it's the simpler sign domain. We have the abstract transfer function for the multiplication, and we all know that the multiplication is complete for the sign domain. So 1 times 2 is 2. That is abstract to positive. Positive rule of sign positive multiplied by positive is positive. So we have completeness, and we can do the same for other example. And the multiplication is complete. We cannot do the same for the addition. Indeed, the addition is not complete for the sign domain. Here we have +1 that is abstracted to positive, but here negative plus positive, it is I don't know, because we have positive and negative integers. So this equation does not hold, and we have incompleteness. So this is not complete for the addition. And this is a running example, so this is, we show in some slides why I choose this domain. So the goal of this topic, of this talk, is to show you how we can check completeness or domain precision by using static analysis. So we have this the analyzer that maybe compute the sign. We have a bunch of programs, and this analyzer say, yes, this program is correct, or I don't know. Some of these I don't know are indeed false alarms, and some of these false alarms are due to incompleteness of the abstract computation. So we want to ask for which program is an analyzer complete, and this is basically as this Popple paper say that we have to analyze the analyzer. So we want to analyze the analysis itself. This is quite complicated. And the second question is, can we reason about completeness when we don't have the Galois connection we have seen before between the abstract and the concrete domains? For instance, if we have fine inequalities or automata domains that are not linked by Galois connections. And I'll start by inspecting this second part, the second question. So in the standard classical setting of abstract interpretation, we have a Galois connection between the concrete and the abstract domain. Then this means that gamma is coadditive, so is mean-preserving. But what does it mean? So this means that, of course, gamma is monotone to preserve soundness. But having a gamma coadditive, or having a Galois connection, means that for each concrete object, we can pick up a best correct approximation of this object. So we have two conditions. For each concrete element, we can derive a sound abstraction, and for each concrete element, we can find the best one. But in some cases, we don't have the best abstraction. For instance, the automata domain, we cannot approximate a context-free language with a unique regular language. And so in this case, we cannot reason about, for instance, completeness or other properties of the domain. But we can still define an abstraction. Indeed, these domains are used in practice. And in this case, gamma is not more coadditive, okay? But of course, it must be monotone. But which is the requirement that we must not lose. So we must not lose the requirement that we need a correct approximation of each concrete element. So for instance, here we can map C to this point here, and the abstraction is sound, but we can map this other object in this other element, and we preserve soundness, but we lose monotonicity of the abstraction. And this is a crucial point because the only requirement, the most important requirement we can relax going to from standard Galois connection to weak Galois connection that we define is that we may relax the monotonicity of the abstraction. So we only require soundness for each concrete element, but we don't require we can relax the requirement of having a best abstraction. And this means that we can relax the monotonicity of alpha. And we will use this for next result. So we have an example here. Usually we use these examples, to say, oh, this is a bad domain. You don't do sign in this way. And actually, it is true. It's not a domain in the classical sense, but it is a good example for weak domain. Of course, here we map gamma in this way, in the most intuitive way, and it is monotone, okay? But how we abstract 0? In this case, we have two options. We can map 0 to this guy or to this guy, but there is no best one. We cannot pick the best abstraction for 0. So in this case, we have a family of abstract functions we can use, and how we select this function or how we select the weak domains is crucial in developing an analyzer. And they are not monotone, of course. But can we still reason about these domains? Yes, we can try it. So this is the transfer function, the abstract function for the multiplication that was complete for the same domain. And it turns out that if we choose this alpha 1 here, then we lose completeness for the multiplication. Okay, this example works, this other example works, but here if we multiply -1 times 0, we obtain, of course, 0 that is mapped to positive, but here we have negative times 0 that is mapped to positive, so negative times positive rule of sign is negative, so we lose completeness for the multiplication. But instead, if we select the other option, then we still we maintain completeness for the multiplication because now this guy is mapped to to negative, and we have completeness. So we have a way to select a best weak domain in order to satisfy, for instance, completeness. Or we may change the domain at runtime when we run our analysis. And we started investigating from a theoretical point of view weak closure, so weak abstract domain, as we do in the classical setting. And when, of course, we reduce a Galois connection to a Galois insertion by making gamma injective. So in the weak abstract interpretation framework, let's say, so weak domains, when we maintain the extensivity of gamma after alpha, and we maintain idempotence. But we lose again monotonicity. So the only difference between weak domains and non-weak domains or domains is the lack of monotonicity. And this is helpful, very helpful, because we can reuse techniques, construction proofs that we use for standard domains in the weak setting if we don't use monotonicity, for instance. So a weak closure is basically an upper closure operator that is not necessarily monotone. And we start reasoning about this stuff, but it is just initial work. Here we have two examples of weak domains. So if you can see here, we lose monotonicity. And of course, we can compare weak closures as we do with standard closures by pointwise comparison of between functions, and we may define the postset, the partially ordered set of weak abstract interpretation. We have to investigate more if maybe we can end up in a lattice or do some more technical stuff on this topic. But we have a negative result. But you can, this is indeed a counterexample. Upper closure operators can be uniquely identified by the set of their fixed points. But we cannot do the same with weak closures. Indeed, these two weak closures have the same set of fixed points, but they are different. So we lose this nice property of weak closures, of closure operators. Now let's jump to the other question. How can we derive a static analysis to check completeness? Well, completeness, as we said before, involves the abstract the computation, so the analysis, the analyzer. Indeed, it is a property. We want to check a property of the analyzer. Indeed, this is okay. The definition of completeness written in terms of upper closure operators, and here rho after f after rho is basically the analysis, so the analyzer. So in this equation, we have the analysis, and so we have to check a property of the analysis, but this is quite difficult. Checking the analysis, the analyzer is quite difficult, so we tried a way to remove the analyzer from this equation. Can we check completeness only in terms of the program, not in terms of the analyzer? And the answer is yes, and I'll give you a very, very high-level idea. So if completeness holds, then we have that, okay, we apply the concrete function, we go in the abstracts, and we have the commutativity, so this is equal to the abstract function. But we have a universal quantification, so we can do this reasoning for another point, x2. But what happens if we impose that x1 and x2 have the same age under rho? Well, so these two elements are the same, but f is a function, so these two guys collapse. And also rho is a function, so these two guys collapse. And so basically, if we assume this equation, so if you assume that the inputs of the concrete function have the same image under rho, then we have that the abstraction of the concrete computation is the same. So we removed here the dependency on the analyzer, so we can reason about completeness only in terms of an abstraction of the concrete computation. Well, this is an hyperproperty of the program. So we jumped from a property of the analyzer to an hyperproperty of the program. I won't go into details of hyperproperties, but a special kind of program properties that talks about the partial aspects of the computation. So, for instance, if you want to check a null pointer, check a null pointer exception, you can, in principle, run each execution of the program, possibly infinite set of execution. But if there is a bug, just looking in isolation and on each execution, we will find a bug. So if there is a null pointer exception, looking singularly on each execution, you will find the exception, if there is one. But this is because the bug is defined in terms of single execution. But there are some more tricky bugs that requires different execution, even not only to be verified bounds, but to be defined. For instance, information flow, if you want to check a leak, information leak, you need to compare different program execution or in concurrency requirements. You cannot even define data arrays if you only have one execution. So with hyperproperty, we can model this kind of requirements. And to verify the hyperproperty, we want to look at partially on the semantics of the program. So we have to analyze each subset, in principle, of the semantics of the program. But we can do it with static analysis. We prove it. But which kind of hyperproperty is completeness? If indeed here we have a very common pattern if you work in language-based security, and this is indeed non-interference. So this is okay. We have two different domains in input and output. But you can replace eta with rho, and everything works. And indeed, abstract non-interference basically says that if we have two inputs that are equal and up to eta, and we compute the function on these inputs, then we end up into outputs that are equivalent up to rho. This is a generalization of the Cohen and classic non-interference, but this is exactly the definition of completeness we have seen before. And indeed, of course, we have shown, I give you an idea of one of the implications, and we prove also the other implications. So we prove that completeness is equivalent to abstract non-interference. And this is nice because we can develop some verification mechanism. We have some verification mechanism for non-interference and abstract non-interference. You can reuse them to verify completeness. And this also works in the case of weak domains, because in all construction, in all proofs, we don't use monotonicity. But the only difference between weak domains and a standard domain is monotonicity. So we can apply the same reasoning on weak domains and check completeness also for weak domains. For instance, we can induce completeness for weak domains. Indeed, the complete shell and complete core that has been developed for completeness. I won't go into details, but we can remove some object in the abstract domain in order to achieve completeness, or this is the core, or we may add some elements in the domain to achieve completeness. This is the shell. And these core and shell have been developed in terms of abstract interference. So we can adapt this construction and definition to the weak domain settings. And indeed, we provide in the paper a deductive system for abstract interference on weak domains. That is a slight modification of the one that has been developed for classic abstract interference in 2010. And so we can derive inductively on P syntax and the program syntax the most abstract domain such that completeness holds for the program with this deductive system. But we can do more. We can statically verify completeness even for weak domains. By using hyperanalysis. For non-interference, classic non-interference has been developed a static analysis that based on hypersemantics, so that verifies non-interference. I won't go into details, but we need hypersemantics that computes on set of executions in order to model partial aspects of the semantics of the program. Then we need a suitable hyperdomain, so a domain defined on a set of execution, and then we can verify no interference. With a slight modification, we can do the same for abstract interference, and so we prove that we can build a static analyzer that works, that verify abstract non-interference, and in turn that it can verify completeness. So we can build this static analyzer and check non-interference, abstract non-interference, and in turn completeness for a given program. Of course, we have a false positive also in this case. So to conclude, we basically restated the problem of analyzing an analyzer. So is the analysis for P complete? With a more simpler question, is P abstract non-interference? So we jump from a property of the analyzer to a hyperproperty of the program. So we can verify a property of the analyzer only in terms of the program. This is much more simpler. And we can do it by extra interpretation. And so we can derive an hyperanalysis for P. So we can build an effective verifier for completeness by exploiting the correspondence between completeness and abstract interpretation. And we can do it also for weak domains. So restating Jacobazzi et al. In this paper, completeness is an hyperproperty of the program. And of course, a property of the analyzer. And as a future work, we can extend this finding to other flavors of completeness. For instance, we have the classical notion of completeness, which is global, and as Roberto said before, we can check a local version of completeness when we require the commutativity here only for some points of the domain, not for all. And we can also, we have partial completeness when we relax the equality here, and we allow a little information loss, but this imprecision is bounded by a given epsilon here. And we can formulate all of them as hyperproperties. So in principle, we can verify all these property of the analysis on the program with a hyperanalysis. And this works also in the weak domains case. So we can statically check the precision of a static analysis. We can prove it for completeness, global completeness, by using an hyperanalysis for abstract interference. We are pretty sure that we can do the same with local completeness, because we just have to tune the hyperanalysis to select on which point we can start the abstract computation. And we believe that we can also do the same for partial completeness by using, instead of abstract interference, the quantitative version of abstract interference. So abstract interference basically say there is or there is not leak, information leak. In the quantitative version, we measure how much information is leaked. So for instance, if we leak 1 bit of a password, maybe okay or maybe not. But we can bound this information leak. It's quite related to partial completeness. So we believe that an hyperanalysis for quantitative ANI can be used to statically check partial completeness. And everything works in the weak domains. Again, because in all construction, in all proofs, we don't use monotonicity. As a long-term view, can we generalize the approach to any other analyzer property? If there are any other interesting analyzer properties, we don't know, but probably yes. And we are working on that. So thanks for the attention, and if you have questions.
Questions? Time for a little bit of time.
I'm sorry for the baby screaming. And I'm also sorry for the formulation of the question. I'm not sure I do it in the right way. But so when you talk about completeness, this is for safety property, right? So what I'm getting at is, what if the property that you're interested in is non-interference? Can you do completeness of non-interference with non-interference?
Yeah,
kind of
this additional level of abstraction, let's say. We didn't investigate this problem, but in principle, yes. And this, but we have to investigate more this topic. But it's quite interesting because also the upper analysis can have false alarms, so we can check completeness also for the analysis of the analysis. So.
Okay, thanks.
It's better. Other questions? Double check online here. No. Yes. All right. I guess I'll ask one. I don't know if I just missed this, but like when you're trying to, with these weak abstract domains, do you have to do this kind of domain by domain analysis to figure out, which abstraction to use and so forth, and to get completeness?
Yes. If you want to check completeness, you have to focus on a given analysis. So yes, you have to. Also, in the case of weak domains, you have to focus on a single domain. Yeah.
So like in the example you gave with just the weak sign, just for simplicity, right? Like for multiplication, one of them was complete and one of them wasn't in terms of the abstraction function choice. Can you automate that selection somehow, or is there a methodology? Or
actually not. We don't have a methodology or an idea how we can automate this process, but yes, for now it's totally manual, but you can insert heuristics that force, I don't know, completeness. If you know your program, maybe in the program you have a lot of multiplication, then we can use this alpha, but you have to analyze your domain, your weak domains before. Yeah.
All right. Let's thank the speaker.